5 outboard brands that failed before 1,000 hours, and the 2 that last 10,000. The marine industry rarely publishes failure rate data on outboard motors. What it publishes instead is marketing language about reliability and durability, even on engines that statistically fail before the average buyer has paid them off. 5 specific outboard model lines manufactured between 1997 and 2020 have documented failure rates that exceeded what most owners considered acceptable, with catastrophic powerhead failures occurring well before the 1,000-hour mark. 2 other engine families from the same era have logged between 5,000 and 10,000 hours in commercial fleets running offshore in Alaska, the Gulf of Mexico, and the Bahamas, with original powerheads still operating after 2 decades of continuous saltwater duty. The difference between the failures and the survivors is not horsepower, not price, and not country of manufacture. The difference traces back to specific engineering decisions each manufacturer made and to the public acknowledgments those manufacturers chose to issue or withhold once the failure started accumulating in customer hands. This is the gap between what the dealer told you and what the mechanics actually see. The 5 engines that defined what failure looks like in the modern outboard market, and the 2 that quietly proved what is still possible when an engineering team prioritizes the right things. The first failure on the list is also the one that ended an entire American manufacturer. The Evinrude Ficht is the engine that took down OMC. The parent company of Evinrude and Johnson launched the Ficht direct injection technology in 1997 as the response to coming EPA Tier 2 emission standards. The Ficht system used high-pressure direct fuel injection that was supposed to deliver 4-stroke cleanliness with 2-stroke power to weight. The engineering bet failed catastrophically. The Ficht failure rate on early production engines reportedly exceeded 50%. Some engines failed within hours of being commissioned. One documented owner reported a 2000 Evinrude Ficht that blew up after 19 minutes of total runtime. Others failed at 50, 100, or 200 hours, with the most common failure mode being injector or fuel pump destruction that grenaded the powerhead. Repair costs ran between $3,000 and $10,000 per engine, and the parts supply chain was unreliable because the technology was new and replacement components were not stocked at most dealers. OMC tried to salvage the Ficht through software updates and improved injectors through 1999 and 2000, but the reputation damage was permanent. The company filed for bankruptcy in December 2000. The Evinrude and Johnson brand assets were acquired by Bombardier Recreational Products, which later became BRP. The Ficht technology was retired and replaced by the E-Tech platform when BRP relaunched Evinrude in 2004. The owners who had purchased Ficht engines between 1997 and 2001 received no warranty support after the OMC bankruptcy, no recall, and no organized remedy. The engines were effectively abandoned in customer hands. The Evinrude Ficht remains the modern outboard industry's reference case for what happens when an engineering team rushes a major technology change to market without adequate validation. Mercury made the same bet at the same time, and the result was structurally similar but commercially survivable. The Mercury Optimax launched in 1996 to compete with the Ficht and to meet the same EPA emissions deadlines. The early Optimax production runs from 1998 through 2002 had a specific structural problem that destroyed powerheads. The air compressor that pressurized the fuel injection system was the failure point. The compressor unit ran continuously while the engine was operating, and the early designs used materials and tolerances that did not handle the heat load of marine applications. The compressor would fail without warning. When it failed, the injection system stopped delivering fuel correctly, and the engine would either run lean or burn pistons or seize entirely within minutes. The Optimax air compressor failures showed up consistently between 400 and 900 hours of operation. Repair required complete powerhead replacement in most cases, with parts costs running between $5,000 and $8,000 depending on horsepower. Mercury eventually redesigned the air compressor in the 2005 model year, and post-2005 Optimax engines do not have the same failure mode. The early production engines that received the failure-prone compressor were never recalled, and Mercury did not retrofit existing units. Owners who bought a 1998 to 2002 Optimax received no warranty extension on the redesigned components. The Optimax engineering lesson is similar to the FICT in one important way. Both engines used direct injection technology developed under regulatory pressure. Both shipped to market before the technology was fully validated, and both produced failure modes that destroyed powerheads early in the operational life of the engine. The difference is that Mercury survived the failures because the rest of the lineup continued to perform, and the Optimax brand recovered after the 2005 redesign. The next manufacturer on the list took a similar engineering approach with different results. Yamaha tried the same direct injection approach with different engineering and produced a different category of failure. The Yamaha HPDI was the Japanese answer to the FICT and the Optimax. The 150, 175, 200, and 250 horsepower HPDI two-stroke engines launched in 1999 with high-pressure direct injection that was supposed to match the emissions performance of four strokes while retaining two-stroke weight advantages. The HPDI worked brilliantly when functioning. The problem was that the injection system failed at rates that mechanics still talk about more than 2 decades later. The HPDI injectors used proprietary Yamaha components that were not interchangeable with other manufacturer parts. A failed injector cost between $800 and $1,200 per unit at dealer pricing, and the diagnostic procedure required specialized Yamaha equipment that most independent marine shops didn't own. Owners with HPDI engines that started experiencing injector failure typically faced repair bills between $4,000 and $8,000 to replace all 6 injectors, plus the high-pressure fuel pump. The failures appeared most consistently between 600 and 1,000 hours of operation, which placed the typical failure point well outside the standard 3-year warranty period. Yamaha discontinued the HPDI in 2003 when the company shifted its high-horsepower lineup to the 4-stroke F-Series platform. The HPDI was never officially recalled, and Yamaha did not issue extended coverage for the injector failures. The HPDI engines remained in customer hands as boats moved through the secondary market, and mechanics today specifically avoid HPDI-equipped boats when evaluating used purchases for personal use. The HPDI is the reason most experienced mechanics, when asked about Yamaha two-strokes, will specifically clarify they mean the carbureted versions or the OX66 EFI, not the HPDI. Yamaha was about to make a separate engineering mistake on the 4-stroke side of the lineup, and that mistake preceded the most widely documented outboard defect of the past 25 years. The Yamaha first-generation F-Series 4-stroke is one of the most widely documented outboard defects in the history of the marine industry. The F225 and the F250 engines manufactured between 2000 and 2005 carry a defective coating on the internal aluminum dry exhaust passages. The coating broke down faster than the engine was designed to last. Hot exhaust gases burned through the aluminum casting walls. The corrosion was internal and invisible, which meant owners did not discover the problem until the engine started losing power, smoking, and eventually seizing. The typical failure window was between 500 and 700 hours of use. The class action lawsuit filed in 2013 by Clifton Mitchell and Keith Johnson documented repair costs ranging between $3,000 and $20,000 per engine, depending on the severity of the corrosion. Yamaha created an internal repair kit available through authorized dealers, but never issued a public recall, never published a technical service bulletin acknowledging the defect, and never sent notification letters to registered owners. The defect was quietly corrected on later production runs through a supplier change around 2005, but the engines already in customer hands were left without manufacturer remedy. The Yamaha first-generation F-Series remains in the used market in 2026, 25 years after the first affected engines left the factory. And mechanics still specifically check for the exhaust corrosion when evaluating used purchases from the affected production years. The most recent entry on the failure list is also the one that finally ended the brand that started the entire pattern. The Evinrude E-Tech G2 was supposed to be the engine that proved BRP had moved past the FICT era and re-established Evinrude as a serious player in the high-horsepower outboard market. The G2 launched in 2014 with a completely redesigned cowling, updated direct injection electronics, and the same fundamental architecture as the first-generation E-Tech. The first-generation E-Tech from 2004 to 2014 was a genuinely reliable engine. The G2 was not. The G2 ran into a combination of problems that included parts supply issues, dealer support gaps, and specific reliability failures in the electronics package. The water-cooled engine control unit with integrated regulator and rectifier became a known failure point. Replacement ECU units cost approximately £3,000 in the European market, which made any electronics failure on an out-of-warranty G2 essentially a write-off scenario. The fuel injection system also developed problems with ethanol-blended fuels, with injector clogging and high-pressure fuel pump failures appearing consistently between 600 and 1,000 hours. BRP shut down Evinrude production in May 2020, ending more than 100 years of continuous American outboard manufacturing. The G2 reliability problems contributed directly to the decision. The remaining G2 engines in customer hands no longer have factory support, parts supply, or warranty coverage. The brand that built the Ficht and the G2 within 20 years of each other ended its run with the same fundamental problem both engines shared, which was rushing direct injection technology to market without validating the supporting systems that were supposed to keep the technology running. The two engines that did this correctly approached the problem from the opposite direction. Both prioritized validation over speed to market, and both produced reliability records that the failed engines never came close to matching. The same Yamaha that produced the defective first-generation F-Series corrected the design in subsequent production runs and built what is now widely considered the most reliable high-horsepower outboard in commercial operation. The F-Series engines manufactured after approximately 2008 used the corrected dry exhaust coating, improved cooling system architecture, and a 4-stroke powerhead design that has been incrementally refined for over 15 years. The reliability data on these engines is exceptional. Commercial fleet operators running Yamaha F-Series engines in the Florida Keys, the Bahamas, and the Gulf of Mexico have logged consistent 5,000 to 7,000 hours on original powerheads with proper maintenance. Documented examples of Yamaha F225 engines with 6,500 hours still producing rated horsepower appear regularly in commercial sale listings, and mechanic communities have documented Yamaha powerheads reaching 10,000 or more hours when the supporting components are replaced on schedule. The pattern that emerges is that lower units typically wear out first, at 2,000 to 5,000 hours depending on hull weight and operating conditions. Most commercial operators replace the lower unit 2 or 3 times across the life of a single powerhead. The engineering reason for the Yamaha F-Series longevity traces to multiple factors. The 4-stroke design uses a separate oil sump rather than mixing oil with fuel, which means cleaner combustion and reduced cylinder wall wear. The cooling system flows substantial volumes of water through the powerhead at all operating temperatures, which keeps cylinder head temperatures within design parameters, even at sustained wide-open throttle. The fuel injection system uses port injection rather than direct injection, which avoids the failure modes that destroyed the Ficht and the G2. The combination produces an engine that, when maintained with regular flushing and scheduled service, routinely outlasts the boat it was mounted on. The second survivor on the list is the engine that recreational market overlooks and the commercial market quietly depends on. Suzuki is the outboard brand most often overlooked by recreational buyers, and most often selected by commercial operators who actually need to put consistent hours on an engine. The Suzuki DF200A and DF250 4-strokes have established themselves over the past 15 years as the high-hour standard in saltwater commercial applications. Alaskan crabbing fleets, Gulf Coast shrimp operators, and Florida charter captains have logged 5,000 to 8,000 hour engines on original powerheads with documented maintenance records. The Suzuki engineering choices that produce this longevity are specific. The DF series uses a self-adjusting timing chain rather than the timing belt that requires periodic replacement in most other 4-strokes. The lean burn fuel injection system runs cooler than competitor designs, which extends component life on every part exposed to combustion heat. The dual injection system on the DF200A and larger models splits fuel delivery between port injection at lower RPMs and direct injection at higher RPMs, which reduces carbon buildup on intake valves over time. Suzuki also extends a 5-year factory warranty as standard on most current models, with some markets offering a 7-year option that signals the manufacturer's confidence in long-term reliability. The pricing advantage compounds the engineering advantage. A new Suzuki DF250 typically retails between 8 and 12% below the equivalent Yamaha or Mercury, which puts the cost of acquisition closer to the lower bound of the high horsepower market. The combination of lower purchase price, longer factory warranty, and documented commercial longevity makes the Suzuki the value choice for buyers who plan to keep an engine for 10 or 15 years. The disadvantage on Suzuki is dealer density. The Suzuki Marine dealer network is thinner than Yamaha or Mercury in most U.S. regions, which means parts availability and warranty service depend more heavily on the proximity of a component Suzuki shop. Owners in rural areas or in regions with no nearby Suzuki dealer often find themselves shipping engines to distant service centers, which adds cost and downtime to maintenance cycles. The brand is the right choice for buyers who have a Suzuki shop within reasonable driving distance and who plan to maintain the engine on schedule. The 5 failures and the 2 survivors share a pattern that becomes visible only after comparing them directly. The failures all involve manufacturers rushing major technology changes to market under regulatory pressure, then quietly correcting the problems on subsequent production while leaving the affected engines in customer hands without organized remedy. The survivors involved manufacturers that took longer to validate new technology, used conservative engineering choices in fuel injection and cooling, and built support networks that allowed early adopters to keep the engines running for decades. The choice between buying a new outboard and a used one in 2026 depends substantially on which side of that pattern the specific model in question came from. The mechanics who service these engines for a living already know the difference. The marketing departments would prefer you discover it only after the warranty has expired.